Hello, welcome to my opening remarks for the DIRA Workshop at CVPR 2020. This is Li Pingyang. I'm currently an assistant professor of Geographic Information Science and Computer Science at University of New Mexico, with a research focus on geospatial artificial intelligence. But most of the content I cover in this talk is the work I did last year when I was in Los Alamos National Laboratory. I would like to share you the two quotes before going to my talk. The world is one big data problem. We are moving slowly into an era where big data is the starting point, not the end. I want to point out that the current major attentions in the whole computer vision communities are given machine learning and deep learning based methods. I want to emphasize that fundamental computer vision research deserves some attention as well. As we all know, machine learning and deep learning based methods cannot solve every single challenge the world is facing. Actually, the advances in fundamental computer vision research can help significantly improve machine learning based methods. You will see some examples in the rest of my talk. Okay, now let's get started. This slide shows the major components in the talk. The first is motivation. Then I will talk about my recent DIRA work. Finally, I will wrap up with talk with DIRA Workshop summary. The second component includes first I'll introduce some concepts that will help you get prepared to understand the rest of my talk. Then I'll introduce the image representations I proposed, followed by two applications using the image representation. One is image classification, the other is line segment detection. The major motivator behind the project I work on is photo search versus drawing search. What is this? If you ask Google can tell you what it is. Now, what is it? Is this? Google cannot tell because Google can only find some exact copies. So the overall goal of the project worked at Los Alamos National Laboratory is diagram image retrieval, which is to identify and return visually similar images from a query image. For example, if you input this image, it should return both images that are in the database. So if you ask Google, it can tell you the high-level categories is a technical drawing, but do you think these are visually similar? Not at all, right? So when I work on the project, of course, I need to get started some fundamental tasks such as straight line segment detection. So let's see how many straight line segments you see in this simple diagram. 1, 2, 3, 4, 5, 6, 7, right? If we don't count the curves. Guess how many straight line segments machines see? It's about more than 150 teeny line segments in these simple diagrams. So how many corner points you see in the same simple diagram images? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if we don't count the corner points in the curves. So guess how many corner points machines see? If we input the algorithms about corner points detection requires the hyperparameters, how many points you want to return. If I set 100 points, it returns these results. If I ask 50 points, it returns this. You know, this is not robust. So we definitely don't know how many points we want to return, right, when we come into real world applications. So now I'll talk about some recent work I did for the DIRA challenges. I'll first introduce some concepts, get you prepared to understand the rest of my talk. First concept is called data representation. It's a form that how data is stored, processed, and transmitted. For example, this is handwriting digits 8. Behind the image is a matrix of numbers. So the performance of machine learning methods is strongly dependent on the data representation, also called features, to which they are applied. So for example, the same objects, we can use the river branches, we can use the vectors, and we can use the vectors to represent it. The second concept I want to talk about is feature engineering. Some machine learning projects succeed and some fail. What makes the difference? The most important factors are what features are selected and used. So machine learning usually requires feature engineering, but deep learning does not. However, deep learning requires a large set of annotated data. So whether machine learning is better for your projects or deep learning is better for your projects, we don't know, because they both requires kind of heavy labor intensive. So if you already have a large analytic data sets, then maybe deep learning is a good choice. But if not, it's not. Deep learning is not a good option for your research problems. Then if you need to know more about feature engineering, check my paper, recent review paper here. If you click this link, you can go to that paper directly. So the most important concepts I want to cover is image skeleton. It's a central line, 1 pixel wide representation of an object. For example, for this input image, the corresponding image skeleton in this is a thin version of this input image. So image skeleton emphasizes topological and geometrical properties of shapes of objects that presented in an image. So if you want to know more about image skeleton, check my recent paper published in CVPI workshop last year. So the final concept I want to cover is called topological graph. It's a set of nodes and edges. So actually the graph is in our daily lives, we use it a lot. For example, if each node in this image represent a bus stop, then if between the two bus stops there is a road connected, we can use a line to connect them. It also can be used represented like a friendships, social network. If each node represents a person, if this person is you, and then it has one friend, this is one friend of you, then you have a connection, line connected the two nodes. And graph is an intuitive and powerful data structure and data representation framework because it can capture the topological relationships and spatial arrangement among entities that are present in an image. If you want to know more about topological graph, check my paper here. Click the link, you can go to that paper directly. Now I will introduce the image representation I proposed. It's called a skeleton graph. It's a topological graph generated from image skeletons. So you can check my recent paper I published in the KDD workshop last year, called Image Classification Using Topological Features Automatically Extracted from Graph Representation of Images. So let's look at how this image representation works using a simple example. This is input example, then we generate the image skeleton. Then we generate a skeleton graph from the image skeleton. How the skeleton graph are generated from image skeleton is for each node in the skeleton, we use a node represented 1 pixel. Then if the 2 pixels are neighbors, we use a line to connect them. For example, if these 2 pixels are neighbors, we use a line to connect them. Then does this make sense? Okay, this is you can see it's a simple image representation, but you will see it's very useful and effective. So we will see the first application using my image representation skeleton graph for image classification. So again, this paper in more detail of this image classification method is published in my recent paper. And you can click this paper and go to that paper. Then now I want to use the same simple example to show how this image classification work using the topological features. So input image, then we get image skeleton from the image. Then we generate skeleton graph from the image. Then once we get the images skeleton graphs, we can generate the topological features from the skeleton graphs. For example, how many cycles bridge in the topological graphs. More features are introduced in the paper. So if you are interested, please go to check on our paper. Then, for example, this image contains 1 cycle. This image contains 1 cycle, even though it should have 2, but because the humans write the digits in different way, this has. But you will see all methods can capture these patterns. Even it has 1 or 2 cycles if you have enough training data sets, training data. in your data sets. So one more example, the 9 has 1 cycle. It has 2 cycles for this example. So then once we get the image skeleton and get the topological features from the image skeleton graph, then we train and evaluate machine learning models. We use the multiple machine learning models, random forest, support vector machine, and neural network. Then we also did a k-fold cross validation and did a hyperparameter tunings. Then we evaluate the models using best parameters from the hyperparameter tuning. Let's see some advantages of our approach. It can give competitive results with a very small size of training data and are faster to train. Most importantly, it's much less sensitive to hyperparameter tunings, hyperparameter parameters. That's a good thing, right? That means the data scientists don't need to spend a big chunk of time to fine tuning the parameters for their problems, for the data science problems. So let's see the experiments and results. We compared with the topological features with the Hog features, and run on the support vector machine on the minutes data sets. We can see the dotted line means the baseline model, and the solid line means best model. We can see our methods are much less sensitive to the hyperparameter tuning because while the baseline model than the best models are very similar, closer to the in terms of accuracy. Then we can see our methods can reach very good results over 90 when they have a small training data sets. Also, our methods, the topological features, the topological features are very fast to train. It's very need a small chunk of time, but you can see even for the best models. But when using Hog features, the best models requires a lot of time, much more time to train compared with the topological features. Then you might see maybe your topological features methods are tailored for SVM. You will see we also train on random forest, and we can see that even though the plots are a little bit different, but we can see the similar patterns. Our methods can reach pretty good results when small training data sets, and it's much less sensitive to the hyperparameter tuning. It requires much less time to train also for the random forest models. For the Hog, it requires much time to train, especially for the best models. And the same results applies for the neural network as well. When we have small training data sets, we can reach pretty good results, and it's less sensitive to hyperparameter tuning. And neural network, everyone knows neural network is very computationally expensive. So even our topological features requires pretty much time to train compared with SVM and random forest. But again, our topological features based methods are much faster than the Hog features, even for the neural network. Okay, so now we'll go to the second application of my image representation called line segment for line segment detections. Let's first see some examples of how challenges for machines to see the line segments in the diagram images. This is input image. Then the green lines in this image shows the human annotated line segments. Then we can see the state-of-art methods. This is the methods published in the IEEE PAMI 2017. It's called LineLit. Then we can see these machines see a lot of tiny line segments for the input diagram images. So we propose a method called TGG lines to tackle the line segments present in diagram images. You can check this, click this link, you can go to our papers directly. TGG lines, a robust topological graph guided line segments detected for low quality binary images. So let's see some example. Input image, diagram image, we first extract the image skeleton. We can see this part is missing, but actually that's just a display problem because the pixel image skeleton is 1 pixel wide, so it's there. It's just a display problem. So once we get the image skeleton, we generate a skeleton graph from the image skeleton. Then let's see some zoom in detail for the skeleton graph. For the zoom in detail, for the skeleton graph. We can see for each pixel in the skeleton, we use one node to represent it. Then if 2 pixels in the image skeleton are connected, then we use a line to connect them. Then after we get the skeleton graph, we detect salient points from the skeleton graph. If one pixel has 3 neighbors, we call it junction nodes. If if 2 nodes has sharp turning, for example, if the 2 nodes has 90 degrees, then we represent it as a turning node. Once we get detected the salient points, we use the salient points to segment the skeleton graphs into different passes. For example, this zoom in detail has 3 passes: the orange, the pink, and the gray one. Then once we get the segmented passes, we use our algorithm to simplify the passes that organized by line segmented connected graph. For each passes, we compute the nodes, extract nodes in the passes, and then the little n represent the number of nodes in the pass. Then if the nodes in the pass is more than 2, we compute the convex hull. Then we compute the epsilon. This is our adaptive single parameter in our algorithm, which is computed by the area of a convex hull divided by the perimeter of a convex hull. Then we use the Douglas-Pook algorithm with the parameter we computed to simplify the parse. Let's see how the Douglas-Pook algorithm works. For its input is a sequence of points. Then we calculate this distance. For example, this points to the distance of the line segments of its neighbor points. If the distance is larger than the epsilon, then we drop this point. We do the same thing for each point in the input point sequence. Then we will get a simplified line segments, which is the solid points in here. And then the gray points and the dashed lines, the gray points are dropped. Then this example shows the detected line segments using our TG lines organized by line segment connected graph. This image shows this figure shows how the line segment connected graph works. For each passes in the line segment connected graph, for each passes in the original skeleton graph, we use a points nodes to represent if the 2 passes are connected. For example, connected, we use a line to connect them. Then let's see some experimental results. We benchmark with the 4 state-of-the-art methods, including line segment detector. This input example, the results from the LSD is demonstrated in this figure. We can see the line segment LSD often detects double lines for the line segment in the diagram images, and also has often the double lines are broken because of zigzag noises. For the line-lit one, you can see this is the most recent line segment detector methods published in TPAMI in 2017. You can see this line-lit is much worse than LSD. It has more broken line segments, and it's also some line segments are missing, especially for this part. And our TG lines works the best. You can see it has a clean and clear line segments detected. Let's see another example here. This is input example diagram images. Then LSD means line segment detector. ED line means ED edge join lines. Again, the LSD works has detected double lines, broken lines for the line segments in the diagram images. The ED lines is much worse than LSD. A lot of line segments are missing and it's broken. Then our TG lines works the best. It's obvious. And check our paper for more. We benchmark with the 4 state-of-the-art methods: PPHT, LSD, ED lines, line-lit. You can find the full name of the methods here. Then and more examples in our papers. You can see our example works the best. Our method works best. Let's see some advantages of TG lines. Our TG lines outperforms the 4 state-of-the-art methods for line segment detector: PPHT, LSD, ED line, line-lit. Most importantly, our TG lines only requires one parameter and it's adaptive. Most of the methods, state-of-the-art methods requires multiple parameters, and most of them are not adaptive. Also, all line segment detectments detected by digital lines are organized by a line segment connectivity graph, and not just a loose set of segments provided by other state-of-the-art methods. So you may ask, why digital lines work so well? The main reasons that state-of-the-art methods fail is because of the persistent zigzag noises in low-quality images. And also, the most state-of-the-art methods are built on either edges or local gradients. Our TDG lines can handle zigzag noises very well by leveraging topological and geometrical analysis, and our methods does not rely on edge detection or local gradients. Check our paper manuscripts for more details about our methods. For more details on diagram image retrieval and analysis challenges and opportunities, please check our DIRA paper titled here. You can access this link for the paper manuscript. You can access link for the talk and video and slides for this paper. I want to thank the DOE grant I received when I was at Los Alamos National Laboratory. And I also want to thank my summer intern graduate students, Catherine Potts, Mingong, and Manish. Especially the two female students, they are working very hard and very creative. I have two papers for each female students. Now I want to talk about some summary about the DIRA workshop. The DIRA workshop at CVPR 2020 has 6 organizers, 7 keynote speakers, and 7 executive papers across 22 authors and 20 high-quality program committee members. We have 3 very supportive and generous sponsors. We have 1 Best Paper Award and 1 Best Review Award. For details about the workshop, can find on our website. For the paper manuscript, can find this link, and for the talk slides and recorded videos for the keynotes and the papers, can find at this link. Most exciting moment, award announcement. So the best review award for our DIRA workshop is Xin Chaopeng from Boston University. Congratulations, Xin Chao. The judging criterion is based on qualities, review qualities, promptness, and the number of papers reviewed. The recipients for our DIRA Best Paper Award is Zach Yu and Adriana Kovashaka from Google and University of Pittsburgh for their paper, Seeing Such, Interactive Image Search with Attribute Condition Synthesis. Congratulations, Zach and Adriana. The judging criteria are relevance to DIRA and 3 reviewers' ratings and 3 reviewers' confidence. I want to thank the 6 workshop organizers and 7 keynote speakers and 20 program committee members and 22 DIRA workshop DIRA authors and 3 very supportive and generous sponsors: NVIDIA, Intel, and Advanced at UM. We also want to thank CVPR chairs and workshop chairs. Without you, we cannot make our DIRA workshop as a successful event at CVPR 2020. Thank you. Thank you. I look forward to your questions in the QA sessions. Take care.